It stands 3,000 meters above the Arizona desert, gazing into the night sky. Its giant mirrors can pick up light from stars 9 billion light-years away. Thanks to it, astronomers can see further into space than ever before. The Large Binocular Telescope is the biggest optical telescope on the planet and the culmination of over 300 years of engineering genius. It owes its success to 6 historic advances in the telescope world. At the heart of each lies a major technological innovation that allowed astronomers to build bigger telescopes. One by one, traveling up the scale, we'll reveal the incredible stories behind these optical giants. And the inventions that allowed them to grow ever larger. Six ingenious leaps forward that enabled telescopes to grow from big to bigger into the world's biggest. As the sun sets over the Arizona desert, the Large Binocular Telescope, or LBT, moves effortlessly into position.
LBT, this is David.
Astronomers make their final checks. Observation is about to begin. Tonight, a team of astronomers led by Dr. Richard Green will gaze inside galaxies on the other side of our universe.
We can look into the cocoons in which new stars and planetary systems are being formed. We can look into the hearts of nearby galaxies, and we can look at the constituent pieces of galaxies in formation.
These observations will help them understand how our own solar system was born. The LBT is the ultimate leap in a series of historic engineering breakthroughs. To understand how astronomers are able to see so far into space, we must step back in time. Our story begins in 17th century England with an earth-shattering invention, the reflecting telescope. Cambridge University, 1669. A brilliant 26-year-old mathematician is starting to think about the universe.
Sir Isaac Newton is one of the most remarkable scientists who ever lived. He was capable of addressing a problem and worrying it for months and years on end. Many people would, of course, get bored with something or give something up. He had that extraordinary persistence. And he starts to work on a number of key problems in physics.
One such problem is the performance of the telescope. Astronomers want to study the planets of the solar system, but their telescopes aren't up to the job. To see these faint, distant objects in the night sky, telescopes will have to capture more light, and for this, they will need bigger lenses. The purpose of the lens is to focus all the light to a single point. But a bigger lens leads to big problems for the early astronomers. Newton had discovered that shining light through a piece of glass bends the light and splits it into different colors. The same thing happens when light is passed through a glass lens, but the lens brings each color into focus at a different point. These multiple points of focus cause the image to appear blurred. The bigger the lens, the more the image will appear out of focus. In his Cambridge study, Isaac Newton believes he's found an answer to the problem, a way to make a telescope which produces crystal clear images without the colors blurring. He removes the troublesome lens and replaces it with something entirely different.
This is the world's first reflecting telescope, made by the young Sir Isaac Newton in 1671. He made it in his rooms in Cambridge from perfectly acceptable ordinary materials of the day: cardboard tubes, a wooden ball to do the adjusting with, but a mirror replaces the lens down here.
Newton's mirror is a metal disc polished into a concave shape. It reflects the light from distant objects to a single point. A second, smaller mirror then bounces the light into an eyepiece. Because the light does not pass through a thick lens, there is no separation of colors, and the image is not blurred. By reflecting the light, Newton's telescope produces the sharpest images in the world.
And that telescope made people's jaws drop in the Royal Society in January 1672, because it was more powerful and gave a better and clearer image than a conventional telescope of 6 feet long.
From this point onwards, the story of how telescopes evolve is a story of mirrors, not lenses, getting bigger. In the world of telescopes, size matters. The larger the mirror, the more light it can capture. The mirrors at the Large Binocular Telescope are as big as they come.
This telescope consists of two 8.4-meter primary mirrors. They collect the starlight falling on the Earth, bring them to a focus so we can grasp the very faint signals from these very distant objects.
By using the mirrors in tandem, the astronomers are able to gather twice as much light and from a much wider field of view. The light is reflected off the surface of each mirror to a single focal point. A pair of highly sensitive digital cameras, each costing over $1 million, then pick up this light.
This is not like a commercial CCD camera that you can buy. It's optimized for very low light. It has 4 9-megapixel CCD chips in it that record a field of view about the size of the full moon. They're in a vacuum can, they're cooled to liquid nitrogen temperatures, and they're exceedingly sensitive at low light levels.
Rather than trying to collect light from the whole spectrum, each camera is finely tuned to detect just half of the colors. These pictures are then combined to produce a far higher quality image than could ever be made with a single camera. The LBT is light years away from the days when Newton looked at heavenly bodies directly with his eyes. Back in 1996, before the mirrors and cameras were even made, engineers in Arizona began to build an enclosure to protect these precious objects from the elements. More than 1,400 tons of concrete ties the building into the peak of Mount Graham and provides a platform high above the trees on which the telescope can stand. 4 huge trolleys mounted on a circular track allow the enclosure to rotate perfectly in time with the telescope. While Newton's prototype was knocked up from cardboard tubes in his college rooms, the LBT will require over 2,000 tons of steel and glass and will take an army of engineers almost 10 years to build. Back in 1672, Newton's reflecting telescope enabled astronomers to get their first clear view of our solar system. But to see deeper into space, engineers building the 180-centimeter Parsons telescope in Ireland must learn how to make bigger mirrors. In 1839, Irish astronomer William Parsons begins to design a huge telescope. He hopes it will help solve one of the mysteries of deep space. Astronomers have observed strange luminous clouds in the night sky. Parsons wants to find out what they are made of.
Were they made up, let's say, of glowing particles of dust or gaseous matter? Or were they made up of infinite numbers of stars, so far away that you couldn't see a single individual star and only emitted a weak light? So what do? You build a giant telescope.
To have any chance of capturing the light from these faint specks in the sky, Parsons needs a giant mirror. In the time of William Parsons, telescope mirrors are concave, like shaving mirrors, laboriously ground by hand. Someone who knows all about mirrors is Dr. Maggie Adarin Pocock, an engineer who fits them into space telescopes. Since her teenage years, she's been grinding her own telescope mirrors.
So, with these two pieces of glass, if you sprinkle some abrasive powder between them and then rub the two surfaces together, if you keep on rubbing and rubbing and rubbing, the two surfaces of the glass change shape. The top one becomes concave and the bottom one becomes convex. Mirrors like this, made by hand, are actually some of the highest quality mirrors because of the random nature of the movement.
This random motion means that any slight mistakes will be smoothed out over time to create the perfect concave mirror. But Parsons' mirror is too big to grind by hand, so he designs a machine to do the job. He uses a steam engine to rotate the metal mirror to be. Then he lowers an abrasive disc onto the surface of the mirror and connects it to a pair of arms. A revolving wheel moves one arm, which in turn shifts the grinding disc to and fro. A second wheel disrupts this steady movement. This irregular motion replicates the randomness of the human hand. The completed mirror is enclosed, not this time in cardboard, but at the bottom of a great wooden tube, 17 meters in length. The tube is suspended on chains between two massive stone walls. Counterweights allow it to be lifted with ease towards the heavens.
When this telescope was opened in 1845, it was one of the great scientific events of Victorian England. The great and the good were here. Scientists, philosophers, arts people, and also, too, ordinary people. It was the inauguration of one of the most wonderful great machines in the history of science.
Parsons points his great machine at one of the mysterious luminous clouds in the sky. He sees not dust, but stars. Today we know that he was looking at the Andromeda Nebula, a galaxy neighboring our own made up of billions of stars.
William Parsons' telescope acts as the great stimulus for the next great giant telescopes of the early 20th century, and of course into our own day and age.
It's 1997. Whilst the huge rotating enclosure of the Large Binocular Telescope is still under construction, 150 miles away at the University of Arizona, the team tasked with building the 8.4-meter wide mirrors are trying to find a way to give them a particular curved shape, called a parabola. Creating a parabola with glass is simple, so long as you melt the glass first and give it a spin.
In here, I've got some water, which is representing the molten glass of the mirror. So what I'm going to do is spin it up gently, and as it starts going faster and faster, the centrifugal forces will move some of the fluid outwards, and you get your nice parabolic shape. And there we have it, the parabolic shape.
To do this on a large scale, technicians at the Mirror Lab build a giant rotating furnace into which they load 21 tons of glass. Opticians have to check each piece of the imported Japanese glass for flaws. The furnace heats the glass until it melts, whilst spinning at 7 rotations per minute. Centrifugal forces push the molten glass into a parabola. To maintain this shape as the mirror cools, the furnace is kept spinning for another 12 weeks. Next, the mirrors are polished to create the perfect surface. Even today, the polishing tool is designed to mimic the random action of the human hand.
Normally, if you're doing it by hand, if you're an amateur telescope maker, you rub, you have some kind of grit, and you rub on this surface to make it as smooth as you can. Well, this polishing tool accomplishes those same things. It has pads that you apply to the surface of the mirror, and it rubs the mirror. These actuators apply a different amount of force moment to moment that changes the shape of that underlying surface. That means that each pad is pushing down with a little different force and a little different angle of attack moment to moment as it goes over the surface of the glass.
In the final stages, the polishing tool removes a layer of glass just 100 atoms thick each time it passes across the disc. To complete the process, a thin layer of aluminium must be applied to each disc to create the mirrored surface. Engineers place the glass disc inside a giant bell jar. Powerful pumps suck out all of the air from the jar to create a vacuum. Crucibles on the side of the jar superheat small amounts of aluminium. As the liquid evaporates, molecules of aluminium float through the chamber and condense on the surface of the glass. The vacuum ensures the molecules spread evenly across the entire surface to create a flawless reflective mirror. When freshly coated, the mirrors are able to capture over 90% of the light which enters the telescope. After almost 4 years of spinning, polishing, and testing, the mirrors are finished.
The outcome was spectacular. The deviation from the perfect figure was about 25 nanometers. That's about 1/1000th of an inch, and it's as if the Atlantic Ocean had waves no bigger than 1 inch tall over the entire extent of that ocean. So it's a beautiful surface, and one that, when we put it to use on the sky, we see how good it is.
Back in 1845, the mirrors inside Parsons' telescope enabled him to catch a glimpse of the faintest stars in the galaxy. But to study distant stars in more detail, astronomers building the 250-centimeter Hooker telescope in California must find a way to follow them as they move through the night sky. At the start of the 20th century, astronomers are trying to capture light from stars so far away and so faint they can't be clearly resolved with the human eye, even when viewed through the most powerful telescope. The only way to see them is to photograph them.
When you start to build a telescope for photography, you have to bear in mind that you have to get rid of all the natural little compensations that human perception makes. The photographic plate is brutal. It only records what hits it. It filters nothing out.
The biggest challenge for the astronomers is keeping these dim specks of light in the viewfinder for long enough to get an exposure. The problem is that since the Earth is constantly rotating and the stars stay relatively still, the stars appear to move across the night sky, and staying fixed on a single star is very difficult. Engineers come up with a plan. They mount their telescope on a swiveling frame. As the Earth spins, they rotate the frame in the opposite direction. This movement keeps the telescope locked on a single point in the night sky. But the telescope designers have to ensure the speed at which the frame rotates is perfectly in time with the spinning Earth.
If that telescope is not utterly precise as it moves, then you get blurs on the photographic plates. You don't get individual star images, and blurs tell you nothing.
Luckily for the astronomers, a machine already exists which works in time with the movement of the Earth. For every rotation of the planet, the hour hand of a clock goes round the clock face twice. So in 1906, the designers of the Hooker telescope try using a clock mechanism to rotate their instrument. They use it to drive a giant flywheel, 5.5 meters in diameter. It turns the 100-ton telescope in the opposite direction to the rotating Earth with flawless precision.
So you've got something literally the size of a big machine, much bigger than, let's say, an American railway locomotive or something like that. Yet it's moving with the accuracy of a watch.
It is Edwin Hubble who captured some of the most incredible images using the Hooker telescope's camera. This photograph, a shot of the Andromeda Nebula, revolutionizes our understanding of the universe. Hubble calculates that the nebula is around 1 million light-years away, much too distant to be part of our galaxy. It must form a galaxy of its own. Hubble is the first person to prove that ours is not the only galaxy in the universe, but one of millions. At the Large Binocular Telescope in Arizona, the mountaintop enclosure is now complete. But before the two giant mirrors can be installed, the team must perfect the mount, which will allow them to move the telescope with flawless precision. Usually, a film of lubricating oil between the bearings would do the trick. Dr. Andrew Shidlow demonstrates.
I have here two plates of glass, and they represent the actual bearings themselves. On top of the bearing, I put a 5-kilogram weight on these two plates of glass, and they're touching. And I now try and move the 5-kilogram weight by applying some force. You'll notice that the stick initially bends and, of course, subsequently breaks. Now, if we repeat the experiment, but this time putting on a few drops of lubricating oil in between the glass plates. If I now place the glass plate on top, you'll notice that the oil spreads out into a very thin film. We now put the weight on, and we now try and push it, and you'll notice that with the lightest touch, it slides off and falls off. So this is the principle, a very thin layer of oil with huge forces holding the molecules together. These forces are able to withstand massive mechanical weights, and thus the bearing is able to work.
But something as heavy as the Large Binocular Telescope would squeeze out a layer of oil. So engineers rest the C-shaped frame on 4 large pads and use high-pressure jets to shoot oil upwards towards the telescope. This constantly replenishes the squeezed-out oil and provides a thin, slippery film on which the telescope can float.
So here we see the motion of this giant structure as it moves in elevation. This C-ring is like a rocking chair rocker. 2 drive motors of about 5 horsepower each on either side are sufficient to move 500 tons of moving weight from horizon flat out to zenith straight up in a minute.
Back in 1917, the Hooker telescope, with its precision tracking, revealed secrets about the universe astronomers had never dreamed of. But in their quest to see further, astronomers would have to find a way to get above the urban glow. In the late 1920s, Edwin Hubble is still measuring the distances to faraway galaxies, and he's noticed something strange. The stars seem to be moving away from each other. This suggests that the universe is expanding. Astronomers decide to build a telescope big enough to test Hubble's theory. This telescope will have a mirror twice the size of any other. There is only one glassworks in the USA with the required expertise to build the mirror. But the works is on the east coast of America, not the ideal place to locate a telescope. Just like today, the bright lights of cities such as New York were creating a glow in the skies above, and this light pollution makes it difficult to see the stars. Finally, the designers find the perfect location. A mountain so far away from city lights, it has some of the darkest and clearest skies anywhere in America. The only problem is that the mountain is in California, over 3,000 kilometers away from the glassworks in New York State. Engineers will have to find a way of getting the mirror across America.
This was a major logistic exercise. The whole thing weighed a great, great deal, and it was probably the most ambitious piece of glassmaking ever made. Of course, the way of travelling in those days was the railway.
But there are no rail cars wide enough to transport the 5-metre wide load if it's laid flat. And standing the mirror upright would make it too high. To fit the mirror vertically on the car, designers need to reduce the overall height. They shrink the wheels by 18 centimeters. Then they build a well in the middle of the car so the disc sits just above the rails. They line the car with rubber to absorb shocks and weigh it down with steel girders to prevent the top-heavy carriage tipping over. Only now do engineers feel confident to embark on the perilous journey.
As it crossed the continent, people turned out in droves to watch it go past. People were enchanted by this great spectacle, this brilliant piece of American engineering crossing the continent.
But not everyone is enchanted with the mirror, as the astronomer after whom the telescope is named soon discovers.
George Ellery Hale, of course, was the patron of the great instrument, actually made the comment to an American newspaper that with this telescope you could perhaps see so far back in time to the very earliest galaxies, you may see the footprint of the Creator. You may see the very beginnings of the universe, God's creation. Now, rather sadly, as it was being conveyed across the continent, there were certain very, very small fundamentalist groups that didn't like this idea.
Railroad engineers fear that fanatics will take pot shots at the mirror as it travels across country. So they protect it with a bulletproof case made from 6mm thick steel. By June 1948, the massive mirror is safely housed in its enclosure. Astronomers begin to use it to test Hubble's theory that the universe is expanding.
Perhaps the most important thing that the Hale telescope told us is that the universe had probably started from a Big Bang.
The telescope collects enough data to show that all the stars in the universe are moving away from a single point. This suggests that everything in existence started at that one point, and then a cataclysmic event propelled everything outwards. This event was christened the Big Bang. October 2003. The astronomers at the LBT are eagerly awaiting the delivery of their giant mirrors. Although they will not have to travel as far as Hale's great disk, the team still have to transport them to the top of a mountain over 3,000 meters high. This journey also runs the risk of being sabotaged. But this time, the threat doesn't come from religious fundamentalists. It comes from environmentalists.
We're in the middle of a United States national forest. And when you drive into a national forest boundary, it says land of many uses. And it turns out that different groups had different visions for what the use of this mountaintop should be.
A group of militant environmentalists argue that the telescope has desecrated a national forest. Suddenly, their wrath has a focus: the mirror convoy. A police escort protects the precious load until it reaches the foot of the mountain. But once there, the team face their biggest challenge. The road to the top is narrow, full of switchbacks and lined with trees. The movers can't cut back a single tree to ease the way. They calculate that if they place the mirror box at an angle of 60 degrees, the load will be narrow enough to fit between tree trunks and low enough to clear overhanging branches. But with a treacherous climb ahead, this precarious angle poses problems of its own. With such a high center of gravity, the slightest tilt could cause the load to tip, flattening trees and destroying the $10 million mirror. To keep the trailer level, the team fit hydraulic pistons to each truck wheel. This allows them to adjust the angle of the trailer as it climbs the steep road and keep the mirror at the correct angle at all times. As the mirror nears the summit, wind speeds reach 100 kilometers an hour. Yet the crew battle on, and the mirror makes it to the enclosure, safe and sound.
In 3 days, they brought up the steel mirror cells and each of the primary mirrors when they were ready, and everything arrived in perfect condition. So it was an impressive challenge that was well met.
And not a single tree was damaged in the process. Access to high ground gives astronomers a clearer view of the night sky. But at high altitude, freezing nighttime temperatures create havoc with their delicate apparatus. So to locate their new telescope higher than ever before, Soviet engineers must find a cool solution to the problem. In 1966, the Hale telescope in America is still the biggest in the world and gives the US an unrivaled view of the universe. Not to be outdone, the Soviet Union wants to go bigger, higher, and even more remote with the Bolshoi telescope. They choose the Caucasus Mountains in southern Russia. Nighttime temperatures up here fall well below minus 10 degrees Celsius. The thick metal walls of the telescope enclosure lock the heat from the afternoon sun inside, keeping the apparatus warm. But when the doors open for observation, the cold night air rushes in, causing the temperature to drop. This cools the mirror down, and it begins to contract, distorting the perfect surface and blurring the image. Dr. Maggie Adair in Pocock explains how changing temperatures can throw out an astronomer's readings.
Now, I've got this fruit bowl which represents my mirror. And what I'm going to do is I'm going to make a parabola on this surface. And to do that, I'm going to apply a vacuum. So now this curved surface represents the mirror of the telescope. Now, we get light coming in from stars billions of miles away, and that's represented by these lasers. So I'll just tweak those on. And I've got them reflecting onto the parabolic mirror, and I can see that I can bring the light into a nice tight focus. So I bring this screen in. Now, I've got the 2 points of light focused together on the telescope, so I've got a nice sharp image. The problem is, if I introduce some heat to the mirror, the 2 spots of light lose focus, they separate, and that results in a blurry image, which is useless for astronomy. Now, I've taken the heat away from the telescope, so this could be opening up the dome in the evening, but the 2 points of light are still separated, because they'll take a long time to recover. And so this is just a fruit bowl, but if we scale this up to a telescope 6 meters in diameter, we're talking a long time to bring those 2 points of light back into focus. And that's one of the problems we experience on the telescope.
To solve this problem, Soviet engineers at the Bolshoi telescope must keep the temperature of their mirror constant. They install cooling units next door to the dome. Fans suck in the relatively warm daytime air and shoot it over pipes that contain cold gas. This cools the air down to nighttime temperature. Pumps then propel the cool air into the dome, reducing the temperature to match conditions outdoors when the enclosure opens in the evening. Astronomers at the Large Binocular Telescope in Arizona share the same concerns as their Russian counterparts.
We are on the top of a 10,500-foot summit, which has a very continental American climate. In wintertime, it gets down to single digits in Fahrenheit, minus 15, 16 centigrade, with a good stiff wind, and in the summertime, it can be as balmy as 60 or 65 Fahrenheit in the upper 20s centigrade.
Rather than cooling the whole building, the engineers decide to simply cool the mirror itself. They take advantage of honeycomb-like cavities built into the back of the mirror. They shoot cold air through tiny jets into these cavities. This cools the mirror from the inside, keeping the temperature constant and preventing the front plate of the mirror from bending.
That allows us, within a very short time, to get the front plate, that 1-inch thick plate of glass that forms the perfect surface of the mirror, to be in equilibrium with its surroundings.
Back in 1975, air-conditioned mirrors allowed astronomers at the Bolshoi telescope to make accurate observations on even the coldest nights. Only one more obstacle now stands in the way of the perfect view of the universe. To build the Large Binocular Telescope in Arizona, astronomers need to find a way of clearing a path through the Earth's dense atmosphere.
When we look up at the night sky, we often see stars twinkling. Now, this is very beautiful for us, but it's a real pain for astronomers. The twinkling is caused by atmospheric turbulence. Light actually travels faster through hot pockets rather than cold pockets of air, and this causes the twinkling. What we've got set up here is a laser reflecting off this flat mirror onto this piece of card. Now, if I turn the laser on, you can see we get a nice steady spot of light. Now, let's introduce some turbulence.
Maggie places a flame beneath the path of the light to create pockets of hot air, or turbulence.
We can see now that the spot of light isn't steady anymore. It's moving around or twinkling, and that's the problem that astronomers face.
Light rays from the stars travel through space like waves. These waves are always parallel or in phase with each other. Without the atmosphere, the waves of light would reach telescopes on Earth in phase. Telescope mirrors would be able to focus the light to create a crystal clear image of the star. However, as a band of light waves enters the Earth's atmosphere, the waves passing through areas of hot air speed up, while those passing through colder air slow down. This means when they reach telescopes on the ground, the waves are out of phase with one another, leading to the image being blurred. Telescope designers soon realized that putting their observatories on top of mountains is only going halfway to solving the problems caused by the Earth's atmosphere. In a radical move, astronomers decide to eliminate the problem altogether.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
And fasten a telescope to a space rocket.
Why do you want to put a telescope in space? The real reason is it's totally free from all atmospheric and terrestrial interference. It's working in pure vacuum conditions, and you have perfect seeing all the time. And that's worth the engineering.
Standing by for SID separation.
In 1990, Space Shuttle Discovery carries the Hubble Space Telescope into orbit.
Discovery's velocity now 4,300 feet per second.
Floating over 500 kilometers above the Earth's surface, Hubble is free of the atmosphere and the distortion it creates. Even with a scaled-down mirror, Hubble produces breathtaking images of deep space. For one momentous photograph, the astronomers deliberately train their telescope on a patch of sky that looks empty. Then they open the camera shutter for an exposure lasting almost 1,000,000 seconds. This is the result, the deepest image of the visible universe ever taken. What appeared to be a void contains 10,000 galaxies, each with as many as 10 billion stars. But for all its undeniable qualities, Hubble has a serious flaw. If one of its instruments fails in orbit, engineers have to send up a shuttle to fix it. Hardly ideal. The perfect telescope would be land-based, yet somehow able to see through the turbulent atmosphere. Engineers at the Large Binocular Telescope think they have hit upon a way to get crystal-clear images of deep space from the ground. Their idea is to measure the extent to which the light is distorted by the atmosphere and deliberately deform a second set of mirrors to cancel out the effect. These small mirrors will sit above the main telescope mirrors. Behind them will be hundreds of motorized pistons. These will push and pull on the mirror's surface by a tiny amount to realign the waves of light falling on it. When the light waves are bounced off and focused into the camera lens, they will be perfectly parallel and back in phase. This will allow the LBT to produce images 10 times sharper than the Hubble Space Telescope. When this system is installed, the astronomers will be able to see straight through the atmosphere as if it did not exist at all. They will not only be able to see distant stars, but the planets orbiting them as well. By examining these distant worlds, they hope to learn how our planet was formed and how life on Earth began. The Large Binocular Telescope is one of the true wonders of science. Indebted to the innovations and daring of the past, this is the ultimate window on our universe.